Today we are excited to share our new features and updates for Motion Solve or Motion Solutions to focus on major releases only. So this session will cover then anything that we released in 2024.1 and 2025. I'll start off with a brief info on resources before handing it over then to Scott, who will cover then updates in Inspire Motion. Then next, Praful will highlight improvements in Motion View, followed by Raghav with updates in the vehicle tools. And then finally, we have Ganesh presenting the latest advancement in Motion Solve. The first resource that I would like to mention is the Altair community. The community entails now all extension to our motion products. Extensions are toolboxes for various industries or verticals. In general, so our products are kept general purpose, but however, sometimes the learning curve is just too steep for newcomers to adopt our products and apply them to the application. And here the extensions come then into play. They're meant to reduce the friction of entry, right? So the latest extension that you will find are provided by the GTT. That means extension can be built independently from the products. That's very exciting. So the ecosystem is then growing. They can also be cross-product related, right? A specific application industry doesn't just need, let's say, Motion View. Sometimes it needs to be combined with HyperMesh, Compose, Activate, etc. So meaning the combining workflows then stretches across various products within the HyperWorks platform. Another great resource I would like to mention is Altair Learnings that includes e-learnings and virtual instructor-led programs provided by the GTT. Today we have a few motion-related e-learnings, but now we want to go to the exciting parts of our products, what we are releasing, and I would like to hand it off to Scott.
Glad everybody could join today. Like Adrian just pointed out, this is a consolidation of the two releases, 24.1 and 2025. Some of you may have seen some of these features and things mentioned on the Inspire What's New. So some of it could be redundant, but if you haven't, we've got some nice things that came into the release. First off, we have design exploration for motion. So it just follows the general workflow of design exploration, but now you have the ability to create variables for certain motion entities, responses for any outputs or components, things like that. If I just go on to the next slide here, you can see, for example, when you're defining the speed of a motor or the actuator length or the stiffness of a spring, you can simply click and create a variable to control that. The supported responses we have, things that are being monitored to compare goals and objectives against during the design exploration, are basically the same things you have for plots. Anything that, almost anything that you can create a plot for, you can also create a response for in the design exploration. Here's a simple example. I had a couple other customer models I really wanted to show, but they're proprietary, so unfortunately I couldn't show them. This was a model sent to me by Europe. They were developing a demonstrator, but basically it's a simple example where we're trying to minimize the torque on the motor, at the same time trying to minimize the torque and find the spring rate that's optimum for that condition. So the nice thing about these is the speed at which these solve. 25 minutes for 20 iterations. There's several contacts in this model. Overall, it's very fast in terms of what you can do. Go away, get a cup of coffee, come back and have your results. This is a video tutorial that was designed for the help documentation, but I see it also made its way onto YouTube. It's got a lot of hits, which is good. I wish I had more time to put together a more thorough tutorial before this, but I just haven't yet. But this is a simple example of catapulting a ball into a box. And you simply vary the angle of the little stop block that's on the arm to make it in the box and optimize it. So it's in the help. There's it's a video based, so you can follow that, and it's very easy to set up the design exploration and run it. I suggest watch the video. Next, we had quality rendering for motion animations now. So the way this is done today is we write out a video file when we set it to the quality render, and we write out a video file. And you can control the resolution of it by changing the maximum samples in here for the rendering. So you can add some nice images, nice animations into reports and things like that. We also have additional input signals for Twin Activate. So we now support displacement and speed for your inputs in here to Twin Activate. Previously, it was only force and torque, but now we have motion-based entities as well. We've also improved the representation of what the multi-body plant looks like inside of Twin Activate. There was some non-clarity in the previous version where we had some additional signals that came out. So we've added some qualifiers in terms of the units, in terms of what these signals are to make it clearer. We've also introduced a new section under the motion preferences. Under Inspire Motion, we have solver units here. So we can set, previously this was under the model units here for the general Inspire setting. But since this is specific to motion right here, and motion models can perform differently depending on the units selected, we've isolated it to motion. On the similar note, we've also set the default units for motion to MMKS. Previously, they were MKS. And overwhelmingly, we had many more models that had cases where they solved faster than the MKS units, or overall, they would converge and the MKS units would not, like you see here. Flex body stress is on by default. Previously, this was a selectable option, but 9 times out of 10, that's what users are doing when they go in here. So it's checked by default, so it's not missed. Just another simple feature to make sure that you get the results you're looking for. Moving into 2025, we have joint limits. So basically, this applies to all joints today except ball and socket. And we can define the limit to how far a joint can translate or rotate. We can do this for both linear and translational degrees of freedom. So if I just click this and play the video, it's just a quick video showing you how we have draggable manipulators. And you can see it's accessed through the joints micro dialog. So we have image plane showing you the extent of the limits. And then here's an example, a scissor lift right here. So lift platform, setting limits on this. Traditionally, we would apply a limit to the motion and we would say how far the motion itself can move. Here I have just a constant force on these actuators and I have limits set for the joints. In 2025, we now also support rigid or flexible bodies of rigid groups. So you simply click on the part and say make flexible. If it's a rigid group, it will highlight all the parts in the rigid group. In addition to the design exploration that I mentioned for 24.1, we now have new design variables coming in 2025 for static and dynamic contact friction coefficients and static and dynamic joint friction coefficients as well. So we're expanding the capability and the variables here for the different things that we can parameterize through the design exploration. We also now enhance this feature. So if you have free joints in a model and you're creating contacts, you can quickly add contacts based on free joints. So you see in this video here, free joints are being added at all the contacting interfaces of all the gear pairs. So I think there was 21 roughly. You can see they're all unknown. And then when you come into the contacts, you can set your filter at free joints. Here I'm just box selecting and creating multiple contacts very quickly. So right there was 21 contacts created within just a few clicks. We also have FMU export. This was previously an experimental feature. We've moved it out as a formal feature. This can be accessed through the input-output signals dialog through the export options. And we can now export an FMU just like we could for Twin Activate. And then finally here, we have display joints as detected features. This was requested by a few customers. The ability, because in a couple releases ago, we changed the joint representation to view the joints as a kinematic representation like you see on the left. But we have had requests to go back and see that original face simply to understand, for example, if you're using analyzed part, what are the faces bearing the loads for that analysis. And also for flex body connection radius in the property editor, when it says entire feature, this is the entire feature that the flex body connection radius is starting with right here. And that brings me to the end of Inspire Motion, and I'll hand it over to Praful to talk about Motion View.
All right, on the motion view side, we have few enhancements and updates for 24.1 and 2025. First, there are a couple of enhancements that assist modeling cables, slender elements such as cables, wires, and hoses. Motion View added support for Motion Solve's deformable curve contact, as well as the radius for the deformable curve. Combined with the Motion View's polybeam feature, these highly flexible elements can be modeled to study interference and range of motions much early in the design. And we also added a capability to add a deformable curve while creating the polybeam itself. In 2025, Motion View added a new capability to store system definitions directly into the entity browser. This offers a very easy way of storing and accessing system definitions, and it assists in creating customer libraries. So a user can right-click on any systems, say store system entity, fill up a form, and then you can provide an icon image, and that system definition will be stored in the entity browser, and you double click on it, it gets instantiated into the model. So it helps in accessing your favorite systems very quickly. In 2024, Motion Solve's frequency response analysis was supported. So this for this functionality, Motion View now has extended the capability to define nonlinear inputs to the frequency inputs. So you can, apart from the constant linear value that we used to give, you can provide a curve, a spline 3D, or an expression as a frequency input. One other change related to run and export, we have defaulted on Python. Motion Solve's Python format as the default for run and export. There is still a choice to shift to XML, but these are the defaults. For the live runs, we always use Python in the backend. So to standardize, we have set Python as the first choice. So to that extent, the run settings and export dialogues have been updated. There are other minor enhancements and bug fixes specific to Motion View. I recommend you all to go through the release notes for 24.1 and 25. With that, I now hand over to Raghav, who has more exciting updates on our vertical solutions.
Okay, good day to all of you. My name is Raghavendra Prabhu, and I am the development manager for Motion Verticals. In the next few slides, we will see a few of the most important features and changes or improvements that we have done for 2024.1 and 2025 release. We'll start with Jupyter Notebook for plotting results. Most of you might be familiar with Jupyter Notebooks. These are primarily used for pre-processing Python code. They can also be used for plotting results or plotting any signals that you have, or writing Python code snippets or text. And basically, they are very lightweight web page application that can be used for various needs. In our case, we are using this as an alternative for plotting reports. The basic idea is that there has always been a vision to let multi-body users see the reports and animations without having to switch to different clients. It's not that we are discontinuing Hyperview and Hypergraph reports. They will remain, but this is an alternative which we wanted to try. And you will see this in 2024.1 and 2025.0 releases. Basically, for all the results that you get from vehicle simulation or vehicle models. These are auto-generated, and you can invoke this from Motion View like you invoke the regular reports. Okay, so what is Jupyter Notebook? So it's an open source web application that allows you to create and share documents. It can contain live code, equations, visualizations, plots, and so on. You can also easily print it out into a PDF and send it to your collaborators or your team members. And as I said, we have deployed this for full vehicle events with Altair driver and suspension KNC analysis, specifically those that include the SDF outputs. And where do you access this in Motion View is on the vehicle tools ribbon. You have the specific icon created here for Jupyter report. So there are 2 satellites which we will see in the following demo. But yeah, it's prominently available and you can access it. To repeat, Hyperview and Hypergraph reports will remain. This is just an add-on. Okay, in this demo, what we are going to see is how do you plot reports using Jupyter Notebook once you have the simulation results. So the usual workflow where you add a model to the session, then you add an event. In the event property sheet or entity editor, you can also see that there is a template for these Jupyter notebooks that have been packaged with the release or with HyperWorks. So now we run the simulation in Motion Solve. Once that is complete, you can access or click on the Jupyter Reports icon and the report should pop up in your favorite web browser. The report templates are exactly same as the traditional report template. You can also see that there are hyperlinked links which have hyperlinks to various pages so that you can easily scroll to the page of your interest. In this demo, what we'll see is the usual workflow that multi-body engineers follow, which is you create various iterations of your model and try to overlay reports so that you can see what the changes that you made in your model, what kind of effect it has on your results. So we load a model here, a front suspension model, which has a KNC event. In this demo, only the ride analysis is simulated. You run the first iteration. Then you make some changes to the model. For the purpose of demo, a random point, in this case, lower ball joint has been edited. And then you run the second iteration. In the beginning, we'll see this is the old workflow where you plot the old report and that still works intact. And this is how you would have overlaid the results. We have a similar workflow for the Jupyter based reports also. You click on the generate Jupyter report option, which is a satellite button, and then you multi-select the PLT files that you want to plot. change the name or provide a save as name, and then you click OK. The report should pop up again. So here what you're seeing is the same report in Jupyter format or notebook format. Also, you will notice that at the end there is the SDF reports. A part of SDF report is printed, which has been discontinued in the traditional reports because text view was discontinued. This is the last demo where we will see if another workflow, which is you plot reports today and then you edit certain attributes of the plots, you scale the curves, you change the time slice of a curve and so on. Most of those things, if not all, can also be achieved using this new report framework. So we begin with a report that has already been created. We just load it. This is the same report from the previous demo. So there is a button at the top called Edit Mode. You can switch it on and you will see some additional buttons which will provide you access to make changes to the report or to the plot or to any attribute of the plot that you would like to see change. So here I believe a scale is changed and you will notice that the y-axis just switched or scaled from 1 to 2. Here we are seeing how we can change the time slice for this particular plot. Also, if you like Python and you want to write some code, edit code, you don't want to go through the UI widgets, you can show the code cell of each plot and then you can make changes here and then apply the changes back. Now let's say you want to add a new page. You can use the add page button. Add all the attributes for that page. Like title, you can change the layout. A few layouts are supported. In Jupyter context, the windows that we are used to in hypergraph are called as subplots. Each subplot can have multiple curves. Here we are plotting coil spring displacement. Apologies for the title being wrong. It's supposed to be displacements. Let me slightly jump forward. So what you see is we have two windows. Each window has two curves and we are setting the attributes for those curves, and then at the end we'll apply the plot. Okay, there is something wrong with the second window, so we can go back to the second window and update that plot. Right. So after you make changes, you need to save, of course, save the page. Okay, that brings us to the end of Jupyter demonstrations. Other topics. So anti-squat and dive outputs have been added in 2025.0. This is an important metric for suspension design, which has been missing for a very long time. We have only added this to the two-wheeler libraries as of now, and these calculations are based on geometry. Some more details. So if you are not aware, squat is the compression of the rear spring when you accelerate a vehicle. If you are a rider or a driver or you are used to driving vehicles, you would easily relate to this. And the dive is an exact opposite phenomenon that happens when you brake. So anti-squat and dive are basically means of designing the suspension geometry so that you reduce the compression of the spring and divert the forces through the joints instead. These outputs have been included in the instrumentation system of two-wheeler libraries. And along with that, you can now also plot dynamic CG height of the model and the wheelbase. Similarly, motion ratios have also been missing for a very long time. Motion ratio specifically for spring has been added in all vehicle libraries, including two-wheelers, small cars, and so on. These outputs are user subroutine based, and these are in all the models that you build using assembly wizard should show these outputs. So motion ratio, again, what it means is how much does your spring deflect compared to how much the wheel center moves. Okay. Again, motion ratios, since they are associated with springs, each spring system will include a specific motion ratio output, which you will see when you build a vehicle model from the wizards. Among other updates, CD tire, we have implemented 2 or 3 new features, which has been in support by CD tire for a long time. Previous time when we tried these did not show promising results, but now they are. So we have CD tire resizing, CD tires magic formula plus, and some changes to the licensing. CD tire resizing is a feature which you can use in your design stage where, let's say, most of your vehicle design is complete, but you would like to see the effect of a small change in the tire size. So to do that, you can use this resizing feature. It needs an extra license. It's very simple to use. In the property file, you need to add this block that you see here, which has the original size and the new size. When you run the simulation in Motion Solve, the size is auto scaled by CD tire, and you can see the results. Okay, so in this animation, what you are seeing in blue color is the original size and the gray color is the resized one. But there are certain limits to this which we need to keep in mind. You should keep in mind, you should remember not to scale the aspect ratio by more than 5% on either side. Rim radius and tire width can be scaled to higher than 5%, but any large change would compromise your results. CD tire magic formula plus is also supported now. It uses the same license that rest of the CD tire features use. This is just an add-on because we have been supporting CD tire for a long time. They had a magic formula also with them, and we thought it's right time to support those. Finally, the licensing changes. CD tire, there are 2 CD tire licenses that we include in our license file and also Fraunhofer provides. One is the regular CD tire license and the other one is the resizing license. 2024.1 onwards, to run resizing, you need to have the regular CD tire license and also the resizing license. This was not the case before, but this is how it is going to be 2024.1 onwards. And again, a reminder, CD tire licenses can be procured from Altair or from Fraunhofer directly. Other notable improvements, steer controller torque based has not been performing as well as the motion based steer controller, which is now almost on par with it. Cosin F-Tire version has been updated to 2024.3 and SimCenter, MF Tire and MF Swift support has been updated to 24.06. There are many more, but we can't include all those here. So please refer to the release notes for all the other changes and enhancements. Thank you very much for your attention. Now it's over to Ganesh for Motion Solve.
The first feature in Motion Solve is real time. You might have seen this in 2024.1. Overall, like Motion Solve 2024.1 had a real time feature where you can simulate the vehicle model in real time without sacrificing the accuracy. This is meant only for a small car and truck for now. And this implementation is really simple for the user. Like user has to just in motion view select one checkbox. It's a one-click automation to convert the wizard model to a real-time model. And these are the steps to solve the model in motion solve real time. This is supported only for the car and small truck library for now. So first the user need to select the car small truck library from the library selection, then build any combination of assembly, add a dynamic event, and in the event editor, there's a checkbox for real-time compliant under analysis parameters. So once you enable this, the model is good to run in real time. So here is an example of the two-door sedan model from the car truck wizard. The model has 383 kinematic degrees of freedom and 19 additional states. So the original model was taking 40.1 seconds. With real time, the simulation wall time was 7.7 seconds for the end time of 10.79 seconds. And you can see the animation is line on line. And I've added few plots, which is the vehicle CG Y, displacement Y, and the roll. Not all step size is real time. Overall, you can expect the end time, simulation end time is less than the wall time. And the advantage of using this real time is you can include all flex bodies, complex geometries, and large number of degrees of freedom in the model. And here is a plot showing that the real time is not dependent on the degrees of freedom. As the degrees of freedom increases, the regular model keeps increasing in the time, simulation time, whereas the real-time model was running within the end time of end time. So this is about the real time. Moving on to the next, we have this frequency response analysis. This was introduced a couple of releases back, and we have done a few improvements on the frequency response analysis, mainly focusing on the NVH applications. So we now have frequency dependent post-hoc modal participation factor, kinetic energy, and dissipative energy, strain energy distribution, transfer path analysis in this releases. So the frequency response analysis with frequency dependent force torque was introduced in 2024.1. Here the frequency dependent force or torque can be defined using the force underscore frequency dependent. This can be applied on any marker. The components or the results components for this force need to be provided by a subroutine, and this subroutine should supply the magnitude of the dynamic stiffness and the loss angle. This force frequency dependent can act on any body, rigid body, flex body, and the point body. We also support a preload expression, which can be a time domain expression, and this has to be used in the FFO sub. And the next feature is the modal participation factor. This can be enabled using the right mode factor, which can be off, on. It can be real or complex. So the modal participation factor measures how much each mode participate for a given frequency in the modal frequency response calculation. And these results are available in the _frf.h3d. The next feature is right energy distribution. So you can write the kinetic energy distribution for all the bodies and the strain and dissipative energy for all the force elements like spring, damper, beams, bushings, fields, and forces. So these results are available in the frf.h3d file. The next major feature is the transfer path analysis for flex bodies. So we calculate the transfer path for all the flex bodies in the model. For this, you need to specify the PF path flex body ID equal to the ID of the flex body. So for this is done in like two steps. The first step is we calculate all the grid point forces on the flex body and we save that. And we cut the flex body and transfer each individual grid point force. We calculate the transfer function for each grid point force to the output response. And these are the outputs in the FRF.S3D. So the items in the green are the request created using the post request. And when you enable the right energy distribution, the items in the yellow are outputted. And the magenta is when right mode factor is enabled. And when you specify the PF path for the flex body, all the blue outputs are outputted, like grid point forces, path participation, point mobility, and transfer function. The next feature is the MKB matrices for from linear analysis. This is a request from the customer. So we as we used to export the ABCD matrices, and now we also export the mass stiffness and the damping matrices in the OML and MATLAB format. This can be used for further FE modeling or stability analysis and control designs. So this can be enabled by using right MKB matrices in param linear statement. The next feature is the higher power contact forces. So this we had a deformable curve contact and deformable surface contact in 2024, and now we also support a higher power force instead of the contact. So we have like 5 new deformable contact forces. One is the contact force between deformable curve and a point. Next is between two curves, between two deformable curves. The other one is deformable curve to deformable surface, deformable curve to deformable graphics, and deformable surface to deformable graphics. So when you have a point, the point can have a radius, and it can be a sphere or ellipsoid based on the radius specified in the XYZ direction. All curves can be represented as a tube with start and end radius. And the force model is linear or linear with stiffness and damping. And you can use also the Poisson contact, where you can specify the penalty and restitution coefficient. The force contact allows liftoff, and the requirement is the contact point should stay within the span of the deformable curve or the deformable surface throughout the simulation. So here is an example for the PTDCV. The next one is deformable curve to deformable curve to deformable surface. This is for the graphics to deformable curve. And the next one is graphics to deformable surface. Moving on, there are a few notable improvements in 2024.1 and 2025. First one is MotionSolve Jupyter Notebook can now show the progress of the simulation. And coming to the results, we have some improvements in showing the sensor ID as well as label in the ABF and MRF. We have added some flags for ABF and PLD to show the comments and labels. And we have a cutoff frequency for linear analysis where you can get a simplified output. You can specify the minimum and maximum frequency. And this cutoff is can be either based on damping or damped frequency or the undamped frequency. Contact COF file now includes the computation time for the contact Jacobian calculation. And some improvements have been made to reduce the contact flickerings. And there is a mode function used to return 5 for both assembly and static analysis. Now we have a new value 35, which is to differentiate the assembly analysis from the static analysis. Same works for get mode function as well. And in MSolve, we have added a vehicle setup utility where you can adjust the mass properties using the optimization and analytically. And you can also visualize the instantaneous center of access instantaneous axis of rotation in MSolve using the raw axis class. So that's all from Motion Solve. Thank you all.